Welcome to this concept explainer, brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Today we are starting a deep dive into a really fascinating topic, the electrostatics of conductors. This is from Unit 2, Electrostatic Potential and Capacitance. And our promise is to give you a very simple, high-scoring, and totally exam-safe explanation. Okay, so let's just jump right in with a kind of puzzle. Imagine you're sitting in a car and suddenly a big lightning storm hits.
Okay.
Now, everyone says that the safest place to be is inside the car or a metal bus, isn't it?
Yes, that's what we're always told.
But the car is made of metal, and metal is an excellent conductor of electricity, so why would it be safe?
That is the paradox, isn't it? I mean,
Yeah.
It's always confused me. If metal conducts electricity so well, the current should just pass right through everything, including the inside.
Exactly. It seems like it should be the most dangerous place to be. So that's the mystery we're going to solve today. But before that, here's another sort of technical surprise for you. Think about a lightning rod on top of a building. It's always designed with a very sharp, pointed end, never a blunt one.
Yes, I've noticed that. But
Yeah.
if the goal is safety, shouldn't we want to avoid accumulating charge? We know that sharp points actually concentrate charge density. It seems like it's doing the opposite of what a safety device should do.
A very sharp observation. And that's the beautiful counterintuitive idea we need to unpack. To understand why that sharpness is actually the genius of the design, we first need to understand the basic principles. Okay, so let's get to the core idea. Everything, and I mean everything, rests on one single fact about conductors. They have a huge number of free electrons. These are mobile charge carriers that can just move anywhere inside.
They aren't bound to a specific atom.
Precisely. So what happens when you put all these mobile charges, which are all negative, together in one place?
They will repel each other
Yes.
strongly. They want to get away from each other.
They want to maximize the distance between them. No. So in a solid body, where is the only place they can go to get as far away from each other as possible?
To the edge. The surface.
To the absolute outermost surface. They literally rush there almost instantly, and they keep moving and redistributing themselves until they reach a state of equilibrium.
A static conductor.
Yes, a static state. And the condition for this static state is that the net electric field everywhere inside the body becomes exactly zero. This creates our electrostatic safe zone.
That makes sense. If they are all pushing each other to the surface, the inside space must be, well, empty of any excess mobile charge.
Let's use an analogy to really lock this image in your mind.
Yeah.
Think of a huge crowd of people who, let's say, really dislike each other. Those are our electrons. And they are trapped inside a large room, which is our conductor.
Okay, a room full of people who want space.
Exactly. They would immediately start pushing away from everyone else. Where would they end up?
All pressed up against the walls, trying to get away.
Yes. They'd be spread out all along the boundary walls, and the middle of the room would become quiet and empty, wouldn't it?
Completely empty and calm.
That quiet, calm middle is the zone where the electric field is zero. The walls are the surface where all the charge resides.
I follow the analogy of charges rushing to the boundary, but I need a bit more clarity on the physics. Why must the electric field be exactly zero everywhere inside? Why can't a small field remain?
That's the key to the word electrostatics. Remember, we are only talking about a situation where charges are static. There's no current flowing.
Right. Static means not moving.
So if there was even a tiny electric field inside, what would happen to those free electrons?
They would feel a force, F equals QE, and they would start to move.
And that movement of charge is an electric current. So for the situation to be static, there can be no net force on the free charges.
Which means the net electric field must be zero. They arrange themselves perfectly to cancel out any external field.
That is the only stable condition possible. It's the definition of electrostatic equilibrium in a conductor. So now that we have this core physical principle, let's see how NSERT formally defines this. This is crucial for your exams.
Okay, the official source says, inside a conductor, electrostatic field is zero. And it adds another point. The interior of a conductor can have no excess charge in the static situation. I understand E equals zero, but the no excess charge part, I'm still a bit fuzzy on that. A conductor is full of positive nuclei and electrons, isn't it? So how can there be no charge?
A very smart question. We are not talking about the protons and electrons that make up the atoms. We are talking about the net charge, or the excess charge that we might put on the body. Let's build the consequences logically, step by step. There are 3 of them, and they all come directly from E inside being 0. So, consequence 1, this is our foundation. The electric field, E, is 0 everywhere inside the volume of the conductor.
Okay, that's established.
Now, consequence 2. This connects the field to potential. Remember the relation E equals minus dV by Dr.
Yes, the field is the negative potential gradient.
So if the field E is 0, what does that tell you about dV/dr?
It means dV/dr is 0. The rate of change of potential is 0.
And if the potential is not changing from point to point, what does that mean?
It means no work is needed to move a charge from one point to another inside.
Perfect. No work means no potential difference. Therefore, the electrostatic potential, V, is constant throughout the entire volume and on its surface.
So the whole conductor is one big equipotential body.
Exactly. And now, consequence 3, which answers your question about the excess charge, this is proved using Gauss's law. Imagine we draw any closed surface, a Gaussian surface, completely inside the conductor.
Okay, an imaginary surface inside the metal.
Yes. Since E is 0 everywhere on that surface, what is the total electric flux through it?
Flux is the integral of E dot dA. If E is 0, the flux must be 0.
Correct. And what does Gauss's law say if the total flux through a closed surface is 0?
It says the net charge enclosed by the surface must also be 0.
Precisely. And since we can make that Gaussian surface as small as we want or as big as we want, as long as it's inside, this proves that there can be no net excess charge anywhere within the volume.
So any extra charge we put on it has to go to the outer surface.
It has no other place to go. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com. Okay, let's do a very simple calculation to check this. Imagine we have a hollow metal sphere. We charge it up so that its surface potential is, say, 10 volts.
Okay, 10 volts on the surface.
What is the potential at the exact center of the sphere?
Well, we just established that a conductor is an equipotential body. So the potential inside must be the same as on the surface. It must also be 10 volts.
Absolutely correct. Not 0, it's 10 volts. And understanding that V is constant inside is vital. It links directly to our next topic of capacitors, which is all about storing charge on conducting surfaces that have a potential difference. Now, this brings us to what I call the silent killer of marks, the biggest exam trap students fall into.
Okay, what is it?
It's this exact confusion between the electric field, E, and the electrostatic potential, V, inside a conductor.
The trap is assuming that because the electric field is 0, the potential must also be 0. I can see how someone could make that mistake.
It is so common. Students forget the relationship E equals minus dV/dr. They are confusing 0 slope with 0 value.
Right.
So just remember this. A flat table has 0 slope, doesn't it? The slope is like your E field, so E is 0.
Okay, a flat table has 0 slope.
But then does the table have 0 height? No. It definitely has some height above the ground. That height is your potential, V. It is constant, but it's not 0.
That makes it very clear. So 0 slope just means constant height. If the conductor is charged to 100 volts, V inside is 100 volts. But if we connect the whole conductor to the ground, then V becomes 0, and E is still 0 inside.
Perfect restatement. That is the complete picture. The potential is only 0 if you define it to be 0, usually by grounding. Okay, let's lock this concept into your memory now with a couple of anchors. The phrase to repeat to yourself is, field is 0, potential is constant.
Field is 0, potential is constant.
And to visualize it, use this physical gesture. Even in an exam, hold your hand out flat, parallel to the ground.
Okay, my hand is flat.
The flatness means 0 slope, right? That's your E field being 0. But your hand is clearly at some height. It's elevated. That height is the potential, V. It's constant, but not 0.
That's a very helpful visual. Flat hand, constant potential.
And this brings us full circle to our car example. This whole principle is the basis of what we call electrostatic shielding.
Or a Faraday cage.
Exactly, a Faraday cage. By enclosing yourself in a conducting shell like a car, you ensure that the free charges in the metal will instantly rearrange to cancel out any external electric field. The field outside, from the lightning, might be millions of volts per meter, but inside the car,
The net field is strictly 0. The charges on the car's surface have canceled it out.
And so, when lightning strikes the car, the massive surge of charge flows over the outer metal surface and goes to the ground through the tires. But the inside...
The person inside is in that safe zone we started with, completely shielded.
Precisely. The car acts as the protective shield. So, to summarize the electrostatics of conductors, let's list 3 final exam-safe facts that you must know. 1. The electric field inside a conductor in a static situation is always 0. Ion equals 0.
2. All excess charge resides entirely on the outer surface of the conductor.
And 3. The electrostatic potential, V, is constant throughout the entire volume of the conductor and has the same value as on its surface. Vin equals V surface. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit profsam.com.
That is PROF Sam, right?
Yes, ProfSam.com. Keep learning and keep challenging the difficult concepts. We will catch up in the next deep dive.